Most of you would be familiar with this picture of linear equations. There are two linear equations, 2x minus y equal to 5 and x plus y equal to 1, and these represent the two straight lines on the graphing calculator. These two straight lines are intersecting at the point 2 comma minus 1, as you can see, and this 2 comma minus 1 also represents the solution to our set of equations. In this video, I would like to introduce the vector picture of linear equations, that is, another way of interpreting linear equations geometrically. So let us start. So we are going to start with the same set of equations, 2x minus y equal to 5 and x plus y equal to 1. Now, we can observe that this set of equations can be rewritten as one vector equation as this. X times the column vector 2, 1 plus y times the column vector minus 1, 1 equals the column vector 5, 1. Actually, you can see that x equal to 2 and y equal to minus 1 satisfy not only both the equations in our set, but it also satisfies the vector equation, which you can easily see by verifying. Now, let us see what is happening in GeoGebra. Let vector A be the vector 2, comma 1, and let vector B be the vector minus 1, 1. Now we can see from the expression here that it is x times the vector 2, 1 plus y times the vector minus 1, 1. And we know that x equal to 2 and y equal to minus 1 satisfies this vector equation. So we are going to plot the vector 2 times the vector 2, 1 minus 1 times the vector minus 1, 1, which here is just 2a minus b. Now let us see where 2a minus b goes. It becomes the vector 5, 1, which you can see in the screen. And what was the desired result? Yes, it's the vector 5, 1 itself. So actually we can see that x equal to 2 and y equal to minus 1 is the correct solution to the set of equations, and it obeys the vector picture as well. So obviously you could try with more examples and see for yourself that the vector picture actually works. Now here is a small challenge coming up for all of you. So we are considering the system of equations x equal to a and y equal to b. This is a very simple equation. You already know the values of x and y. But actually, what I want you to do is to consider the set of equations as x plus 0y equal to a and 0x plus y equal to b, and write the vector equation in the same way as how I have showed you in the previous slide. Moreover, this suggests something very important in vectors itself. So I've given you a hint that the vectors turning up on the left-hand side hold the key to this problem. Are they the basis vectors of the 2D plane, which are I hat and j hat? You could check that out. And of course, you can let me know the solution in the comments. So now we come to the next part of our session, which is understanding the singular case. That is, when does the geometry fail? Most of you would already know that all sets of linear equations won't have a unique solution. They may have infinitely many solutions, or they may have no solution at all. That is why there is some point where the geometry of vectors also fails, which is what we are going to tackle now. We'll start with an example. We'll consider the system of equations 2x plus y equal to 1 and 4x plus 2y equal to 3. In the same way as we did before, we are going to write the vector equation for this as x times the column vector 2, 4 plus y times the column vector 1, 2 equals the column vector 1, 3. Now let us see what is happening in GeoGebra once again. Two vectors on the left hand side were 2, 4 and 1, 2, and on the right hand side the vector was 1, 3, which we have plotted in the diagram. Now we observe that the vector A, which is 2, 4, is just a scaled up version of the vector B, which is 1, 2. What does this suggest? It suggests that if you're trying to express some other vector, say D, in terms of A and B as x times the vector A and plus y times the vector B, you will notice that the vector D is also a scaled up version of A and B, which can be proved easily. What does that tell you is that the vector D also has to be collinear with both the vectors A and B. However, you see in the diagram clearly that the vector C is not collinear with either of the vectors A and B. So in this case, the geometry fails and we say that this system of equations actually has no solutions. This system of equations, which is 2x plus y equal to 1 and 4x plus 2y equal to 3, has no solutions. So the reason for that is that the vector 1, 3 cannot be expressed linearly in terms of 2, 4 and 1, 2. So this is the case where we have no solutions. What about the case where there are infinitely many solutions? How does the geometry fail over there? Now we are considering this set of equations, which is 2x plus y equal to 3 and 4x plus 2y equal to 6. As we have been doing throughout this session, we're going to write the vector equation now, which is going to be x times the column vector 2, 4 plus y times the column vector 1, 2 equals the column vector 3, 6. So now we are going to see GeoGebra how vectors are on the 2D plane. The vectors A and B are the same as before, which is 2, 4 and 1, 2. But now the vector C is 3, 6. As we have said before, vector A is a scaled up version of vector B. Now what we are seeing is that the vector C is also a scaled up version of both A and B. What does this suggest is that the vector C can be expressed linearly in terms of vector A and vector B. That is absolutely true, but the truth is that it can be expressed linearly in infinitely many ways, which we are going to see why. First, we notice that the vector 2, 4 minus 2 times the vector 1, 2 equals the 0 vector, which is 0, 0. So first, we notice that x equal to 0 and y equal to 3 satisfies the vector equation. Why? Because our vector equation was x times the vector 2, 4 plus y times the vector 1, 2 equals the vector 3, 6. So if you put x equal to 0 and y equal to 3, you will notice that it satisfies the vector equation. Now we will add this vector equation 2, 4 minus 2 times the vector 1, 2 equals 0, 0 to our original equation, which is x times the vector 2, 4 plus y times the vector 1, 2 equals 3, 6. If we do that, we will get x plus 1 times the vector 2, 4 plus y minus 2 times the vector 1, 2 actually equals the vector 3, 6. So that means that if x comma y is a solution to our set of equations, then x plus 1 comma y minus 2 is also a solution to our set of equations, which means that in general, you could add multiples of 1 comma minus 2 to x comma y to get infinitely many solutions. So we are going to show an example here. So we know that 0 times the vector 2, 4 plus 3 times the vector 1, 2 equals the vector 3, 6. Also, we can multiply this equation 2, 4 minus twice of 1, 2 equals 0, 0 by 2. And we get the second equation. Now, we can simply add these two equations to get 2 times the vector 2, 4 minus 1 times the vector 1, 2 equals the vector 3, 6. So, 2 comma minus 1 also satisfies the vector equation and hence is a solution. So by adding multiples of 1 comma minus 2, you can generate infinitely many solutions, which is why this set of equations 2x plus y equal to 3 and 4x plus 2y equal to 6 actually has infinitely many solutions. So this was understanding the singular case and how the geometry is affected. So this was the vector picture of linear equations. I hope you enjoyed seeing this video. Thanks for watching, and for more math videos, please subscribe to my channel.